1,700 degrees Celsius.
That is 300 degrees above the melting point of the structural steel used to build skyscrapers.
If you threw a standard car engine into an environment this hot, it would not just fail, it would cease to exist as a solid object.
It would liquefy and drip away like wax running down a candle.
Now, realize that this thermal hellscape is not located in the core of a volcano or on the surface of a distant star.
It is happening right now, just a few meters away from where you sit, every time you fly on a commercial airliner. Inside the high-pressure turbine of a modern jet engine, we are defying the fundamental laws of thermodynamics.
We are running a machine in an environment that is hotter than the melting point of the parts themselves. Logic dictates that the engine should melt.
Physics demands that the turbine blades turn into molten slag and spray out the back of the exhaust.
But they do not. Instead, they spin. They scream. They hold the weight of an entire aircraft in the sky. This is the story of the impossible metal.
To understand why this feat is borderline magical, we must first confront the absolute violence of the environment.
A jet engine is essentially a tube that sucks in air, compresses it 40 times over until the pressure is critical.
The result is a controlled explosion that never ends.
In the heart of this beast lies the high-pressure turbine. This section sits directly in the throat of the volcano, right behind the combustor.
It takes the full kinetic force of that expanding, burning gas. Inside this section, there is a wheel fitted with dozens of curved blades.
These blades are small. You could hold one in your hand. It looks like a simple piece of gray metal.
But when the engine is running at full throttle, that innocent-looking blade is subjected to torture that is difficult to comprehend.
First, there is the thermal load. The gas exiting the combustor is roughly 1,600 to 1,700 degrees Celsius. The sophisticated metal alloy used to cast the blade has a melting point of only 1,350 degrees. Do the math. The air is hundreds of degrees hotter than the temperature at which the blade should turn into a liquid puddle. But heat is only the first villain. The second is the crushing centrifugal force. This turbine wheel is spinning at that angular velocity, the physics of rotation becomes lethal. The centrifugal force pulling. Imagine a piece of metal the size of a smartphone trying to hold up 12,000 kilograms of dead weight, while simultaneously. If the blade fails, the results are catastrophic. It is not a quiet breakdown.
If a blade snaps, it becomes high-velocity shrapnel, moving at the speed of a bullet inside a spinning casing. This results in an uncontained engine failure. Energy release can shred internal mechanisms and destroy the propulsion system entirely. Engineers were faced with a paradox.
They needed a material that could survive forces that tear steel apart, in temperatures that turn metal into soup.
Came from rewriting the atomic structure of matter itself. The first line of defense is not the metal at all. It is fluid dynamics.
If you look closely at a modern turbine blade, you will see it is covered in hundreds of tiny, microscopic holes.
The blade is hollow. Inside, it is a complex labyrinth of serpentine channels.
We bleed cool air from the compressor stage of the engine, air that has not yet been heated by the fuel loop, and we pump it into the hollow core of the turbine blade.
This cool air rushes through the inside of the blade, convection cooling the metal walls from within. But that is just the beginning. The air then exits through those tiny holes on the surface. But it does not just shoot out. The holes are drilled at very specific, shallow angles, shaped like diffusers. When the air pushes out, it creates a thin, insulating blanket of cool air that hugs the metal. This is called film cooling.
The searing hot gas from the engine never actually touches the metal of the blade. It glides over this layer of cool air.
We are effectively wrapping the blade in a refrigerated atmosphere of its own creation. This technique alone drops the surface temperature by hundreds of degrees.
However, film cooling is complex.
If a single hole gets clogged by atmospheric dust or volcanic ash, a hotspot forms and the metal burns through in milliseconds.
We needed a second shield. So, engineers developed the thermal barrier coating. If you hold a raw turbine blade, it looks metallic and shiny. But ready-for-flight blades look beige or off-white. They look like
This is a ceramic material with incredibly low thermal conductivity.
It acts like the heat shield on a spacecraft, re-entering the atmosphere.
It prevents the radiant thermal energy from transferring into the metal alloy beneath. It is a sunscreen for hell.
But even with advanced air films and ceramic shields, the metal inside a jet engine's turbine blades still sits at over 1,000 degrees Celsius. It is glowing white hot. At these extreme temperatures, metal behaves strangely. It doesn't just break, it creeps. Creep is the slow, permanent deformation of a solid material under the influence of mechanical stress. Imagine a stick of butter sitting on a table. It's solid. Now put a heavy weight on top. Inside the engine, centrifugal force pulls on the blade so hard that the metal wants to stretch. It wants to elongate. If the blade stretches by just 1 or 2%, the tip will grind against the engine casing, spark, and shatter. To fight creep, engineers had to look at the metal under an electron microscope. All standard metals are crystalline.
When you freeze molten metal, it solidifies. Tiny crystals start to grow from the liquid until they bump into each other. Where two crystals meet, they form a jagged border called a grain boundary. If you look at normal steel, it looks like a jigsaw puzzle.
For thousands of years, every piece of metal humans used was made of these grains. A sword, a car chassis.
But inside a jet engine, grain boundaries are fatal flaws. At high temperatures, impurities in the metal migrate to these boundaries. They become slippery.
Under the massive pull of centrifugal force, the grains start to slide past each other along these boundaries. The blade stretches. It creeps.
Eventually, cracks form along the boundaries, and the material rips apart.
The engineers realized that the enemy was the boundary itself. If the boundaries are the weak point, then we must eliminate them.
We must create a blade that has no boundaries. We must create a blade that is a single, continuous crystal. The process is one of the most guarded secrets in manufacturing, known as single crystal investment casting. It begins with wax. We create a perfect replica of the blade using wax. We dip this wax into a ceramic slurry, over and urbanization again, until it is coated in a thick, hard shell. We dip this wax into a ceramic slurry, over and over again, until it is coated in a thick, hard shell. We then heat the shell, melting the wax out. This leaves us with a perfect, hollow ceramic mold. Now comes the engineering precision. We place this mold inside a high-tech vacuum furnace. We melt a specialized nickel-based superalloy. This is not just iron or steel. We pour this molten alloy into the mold. If we just let it cool down naturally, it would freeze into thousands of... Instead, the mold sits on a water-cooled chill plate at the very bottom. The furnace is heated at the top and cool at the bottom. We slowly, painfully slowly, withdraw the mold from the hot zone. As the bottom touches the chill plate, the metal starts to solidify. Crystals begin to form at the very bottom. Many crystals start to grow upwards, competing with each other like runners in a race.
But right above the starter block, there is strict geometric gatekeeper. It is a small, corkscrew-shaped passage. As the competitive crystals grow upwards into this spiral, they hit the walls and die off.
The spiral is designed so that only one single crystal, oriented in the perfect vertical direction, can survive the journey through the twist. That one surviving crystal emerges from the pigtail and enters the main blade mold. As we continue to slowly lower the mold, that one crystal continues to grow. It fills the entire blade. It grows around the internal core that forms the cooling channels. It grows into the root. It grows into the tip.
When the process is finished, the entire turbine blade is one single crystal lattice. From the bottom to the top,
There are no grain boundaries. There are no slip planes for the material to slide along. The mechanism of creep is virtually eliminated. This single crystal architecture gives the material superhuman properties. It can withstand temperatures and stresses that would. But the chemistry is just as important as the structure. We call these materials superalloys for a reason. They are.
When this single crystal solidifies, it forms a specific microstructure known as the gamma-gamma prime structure. Imagine a brick wall.
The bricks are hard, cuboidal particles called gamma prime. The mortar holding them together is a softer matrix called gamma.
When the material gets hot, unlike most metals that get softer, this structure actually maintains its incredible stiffness. But the battle against physics is never static. We are constantly pushing the limits. In the 1940s,
Today, we are pushing towards 2000 degrees. Every 10 degrees we add to the turbine temperature translates to massive savings.
However, we are running out of elements. We are reaching the melting point of nickel itself. No matter how perfect the crystal, you cannot heat a material past its liquid phase and expect it to survive.
So, the future of flight lies in abandoning metal altogether.
The next generation of engines is beginning to use ceramic matrix composites. These composites offer superior heat resistance and strength, paving the way for even more powerful and efficient engines. Imagine a material so resilient, it laughs in the face of 2000 degrees Fahrenheit.
Traditionally, ceramics are brittle. Drop a coffee mug, and it shatters.
Ceramic matrix composites solve this, reinforcing ceramic with ceramic fibers, much like rebar in concrete. This creates a material 1/3 the weight of metal superalloys, withstanding higher temperatures without as much cooling air. But for now, the single crystal superalloy blade remains the king of the sky.
It is a testament to human ingenuity. Think about the layers of technology packed into this one object.
Chemistry of rare earth elements, blended to atomic precision. The physics of thermodynamics, managing airflow to create invisible cooling films. Crystallography, growing single stones of metal in a vacuum. And the manufacturing prowess to drill holes smaller than a human hair into a curved surface. Every time you hear the whine of a jet engine spooling up for takeoff, you are listening to thousands of these single crystal blades spinning into a blur.
They are entering a chamber of fire that should destroy them. They are being pulled by forces that should rip them apart. They are entering a chamber of fire that should destroy them. They are being pulled by forces that should rip them apart.
But they hold. They hold because we learned how to trick nature. We learned that to defeat the heat, we had to give the metal a breath of air.
To defeat the stress, we had to eliminate the boundaries between the atoms. To defeat the stress, we had to eliminate the boundaries between the atoms. We took the chaotic, messy reality of metal
and ordered it into perfection. We forced the atoms into line.
The result is a machine that shrinks the world. A machine that makes the other side of the planet accessible in a matter of hours. The jet engine is not just a propulsion system. It is a victory over the limitations of matter. It is the closest we have ever come to building a machine that can survive inside a star.
So the next time you look out the window at the wing and you see the heat shimmer behind the engine, remember what is happening inside.
Remember the war being fought between the fire and the crystal.
Remember that you are being carried through the clouds by a piece of metal that, by all rights, should not exist. But it does.
And because it does, we fly. When the laws of physics stand in the way of human progress, we verify the impossible, and then we mass produce it. That is the power of engineering.